Hi! In today's video I'll be talking about a topic which I avoided for quite a time now. Today I will give you an example about how to use DMA in a Linux driver. But what is DMA and why did I try to avoid it for quite a time now? Well, DMA stands for Direct Memory Access. It's a controller built into your chip which is optimized for transferring memory from one location in your physical address space to another one. The clue about using DMA for memory transfers is, if you're using it, the CPU doesn't have to take care of it and is free to do other computational tasks. Another cool thing about DMA is, it can be triggered by hardware. So let's say we have a UART and the UART is receiving some data. The data reception can trigger a DMA transfer, which will transfer the data from the UART data register into a RAM address. After the transfer is done, the DMA will raise an interrupt telling the CPU, transfer from the UART to RAM has completed. And then the CPU can access this RAM and doesn't have to read out the data over the UART registers itself. So using DMA can be quite a time saver. So why did I try to avoid it till now? Well, using DMA can be quite complex. And even if there is a higher level API available in the Linux kernel, it's still a little bit hardware or architecture specific or dependent. So what I will show you today works on ARM-based systems like a charm, but on my x86 system I didn't get it up and running till now, but I hope this will change soon. So today I will give you a first example about how to use DMA. In this example I will transfer some data from the RAM to another location in the RAM. It doesn't sound much, but it's a first example for how to use DMA. So let's start. Okay, so here I'm connected to my Raspberry Pi over SSH. And the first thing I will do is I will navigate into my Linux driver tutorials folder. In here you can see the various Linux driver tutorials I've already done. Next thing I will do is I will use my simple Linux Kernel Module as a template for today's video. And I will create a new folder I will call 13 DMA Memcopy, because that's what we're going to do today. So let me cd into it. Here I have a makefile to build my kernel module and my module. First I will rename my module to my DMA memcopy.c, and I have to change this in the makefile as well. My DMA memcopy. Okay, and now let's open up the source file. So here we have the description. This is no longer a Hello World kernel module. This is a simple DMA example for copying data from RAM to RAM. Okay, so here we have my init and my exit function, and in the init function I will implement all the code we need. But first we'll need some headers. So I will need a completion, so I will add Linux completion.h. I will need slab.h for memory allocation. I will need DMA engine for using the DMA. And I will need DMA mapping for DMA mapping. Okay, and another thing I will do is I will add a small callback function here, which I will call my DMA transfer completed. And it also gets a void pointer for some data. The first thing I will do is I will create a new completion or struct completion pointer here, and I will cast the pass parameter to this, and then what I will do is I will call completion complete, and I'm passing in here my completion. So this will just finish a completion. So we can use this completion for waiting for the DMA transfer to finish. And I already made an error here. It's just completion, just complete without completion complete. Okay. So much for our callback function. Let's implement the init function in which we'll do the copy. First, we will need a lot of arguments. The first is from the type DMA cap mask t, and I will call it mask. I will talk about these variables in a second when I will use them. The next argument is the DMA channel we will use, which I will call chen for channel. Then I will need a variable from the type struct DMA async tx descriptor, and I will call it channel descriptor. Then I need an argument from the type DMA cookie t, which I will call cookie. Then I will need two variables from the type DMA address t, and I will call it source address and destination address. Then I will need two buffers, one a source and destination buffer. So what we are going to do is we will copy the source buffer into the destination buffer. We need a completion. And last but not least, we will need a status variable. Okay, and let's change this. My DMA memcopy init. Okay, so the first thing we're going to do is we will get our DMA channel, or we will request our DMA channel. Therefore, we first have to decide which kind of DMA channel we want to use, and therefore I will need this mask variable here. With DMA cap 0, I will set the mask here to 0, and then with the function DMA cap set, I will set the capabilities in which I'm interested in, and I will need DMA slave because I will need a DMA slave and DMA private. So the other two variables here, I could pass in a filter function which will filter for the correct DMA channel, and to this function I could also pass some arguments, but as I don't need a better filter here, I can just set both variables here to 0, or both arguments to 0. Okay, and now finally request our channel with DMA request channel. The first argument here is our mask. And then we would have some variables here for our filters too, which I can set to null here. Okay, so let's see if in case channel is 0, an error occurred. And I will print k my DMA memcopy error requesting DMA channel. And I can return with error no device because there is no DMA device we can use here. And after requesting a DMA channel, I also have to release it. So this can be done with the function DMA release channel. Okay. Cool. So now we have requested our DMA channel. Next thing I have to do is I have to allocate the memory for my source buffer and my destination buffer. Therefore, I will use the function DMA alloc coherent. This function will allocate me some memory, but it will also make sure the memory is not cached. So it's actually in the DRAM and not in the cache. And another thing this will do is it will also returns to us, or it will also give us the physical address of the memory we have reserved. Because here the source buffer is using a virtual address, but we will need the physical address for our DMA. So the first argument here is the device for which we want to allocate memory. And as I don't have a specific device here, I will just use my DMA device here. The next argument is the number of bytes I want to allocate, and I want to allocate 1 kilobyte. The next argument is the physical or a pointer in which I will store the physical address of the allocated memory, and this is the source address variable here. And the last argument is the kernel or the allocation flag, and here I will use GFP kernel here. So let's do the same thing here for the destination buffer. Okay. Normally I should take a look if this returns 0, because if so we have no memory left, but in this case let's just say this works to make the code a little bit more easier to read. Next thing I have to do is I have to initialize the code. So I will write 1.2 to my source buffer, and to my destination buffer I will write all zeros, and at the end in both buffers I will have this 1.2 here. And now DMA memcopy before DMA transfer source buffer 0 is, let's print it out. Okay, and let's do the same thing for the destination buffer. Okay. The next thing we will need is we have to get the channel descriptor. So the channel descriptor contains all the information like the source and the destination address where we want to have our DMA transfer, and it also has some more arguments like the data direction or the data bus width which can be used. And to set up this descriptor I will use the following function: DMA engine prepare DMA memcopy. So this function is built for handling DMA memcopy requests. The first argument is the DMA channel over which this request will take place. The second argument is the destination address and then the source address. So these are the physical addresses, right? Then I have to set the number of bytes I want to transfer. And last but not least, the direction. So here it's DMA mem to mem. But for example, if we take our UT example, it would be device to memory instead. So here it really depends which kind of transfer we want to have. Once again, if this is a 0 argument, an error occurred. So I will set the status to -1 here, and I will go to a target I will call free. So here I will declare free, and when I've allocated something dynamically I have to free it, and therefore I can use DMA free coherent. So the arguments are quite similar, so let me copy them. The first argument is the device for which I want to free something. The next argument is the number of bytes I want to free. Then I have to pass in the buffer which I want to free, and then the physical address, and that's it. And of course I have to do the same thing for the destination buffer. Okay. So now we have prepared our channel descriptor, but now we have to apply it to our channel. And this can be done with, or first let's init the completion, and let's set up our callback, because this descriptor also contains the callback function which will be called when the transfer has complete. So here we have a variable called, or a field called callback, and this will be my DMA transfer complete. And the second argument here is the callback parameters which will be passed, and this should be a pointer to my completion. Okay, great. Then the next thing I will do is I will apply my descriptor to the DMA buffer with DMA engine submit. So here I have to pass in the descriptor, and now I can start or fire the DMA transfer with DMA async issue pending channel. So this will start the transfer. Now let's wait for the completion to finish. And I will give it a timeout. So we have our completion and msec to Jiffy's. Let's wait 3 seconds. And if this is smaller or equal to 0, an error occurred. Print k my DMA memcopy timeout. And I will go to release, and I will set the status to -1 here. Here in this release, I will use DMA engine terminate all to terminate all ongoing DMA transfers on this channel, and then with DMA release, then the rest is already here. Okay. Okay, now let's take a look if the transfer was successful. Therefore, I can use, so I have saved this cookie here. And this cookie, over this, I can get the current state of my DMA channel. So with DMA async is tx complete, I can check if the transfer has completed. Here I have to pass in my channel and my cookie, and then 2 times null. I guess these are filter variables too, but I'm not 100% sure. And if the status is equal to DMA complete, I can print out, maybe I don't need this release here if I'm doing this way. I will print out memcopy DMA transfer has completed, and then let's set the status to 0, and let's print out the 2 buffers here once again. And else let's print out error DMA or error on DMA transfer. Okay, so that should be it. But as this is quite a bit of code, I think I've made some errors. So let me try to compile it. Okay, this is looking bad, but let's go over it and let's see what's wrong here. So the first error, this DMA cap set only has 2 arguments. The first one are the flags I want to set, and the second one is the mask. And the rest can be deleted here. Up here I also have a typo. This should be DST address, because in the rest of the kernel module I always use DST address. This has to be channel descriptor, of course, and not just descriptor. And the last error here should be this function call. It's msex to Jiffy's and not msec to Jiffy's. Okay, so let me try to compile it once again. This is looking better. Now let's try to load this module. My DMA memcopy ko. Okay, so no errors. And now let's check the kernel's log. Okay, cool. So first, before the DMA transfer, in the destination buffer we had in the 0 Then the DMA transfer occurred, and now we have a 12 hexadecimal written into the destination buffer. Cool, so that was my first DMA example, but I'm quite sure it won't be my last. So this was a little bit longer video, but I hope you've enjoyed it anyway. In case you want to support my work, you can buy me a coffee on buymeacoffee.com/Linux. So that's it for today. Thanks for watching and goodbye.